I was talking, you are a very interesting person. You were doing
So yes, no doubt. So we will also learn so many things.
No. It was
always lively, energetic.
That period was interesting. 95, 96, 90, when DRDO started building large rockets, right? I mean, it was a very interesting time. Yeah.
Mm.
Okay. Let me.
ভিডিও অফ করা আছে। আচ্ছা ভিডিও অফ করা আছে। এই তো মাইক্রোফোন এই জন্য আসলে মিউট করে রেখেছো। কোথায় মিউট? এই তো এইখানে। ওইখানে মিউট করা আছে।
Now sir has.
Okay.
Yeah.
But now you are audible, Chakraborty sir.
তো চলে যায় তো। আচ্ছা।
We can hear you, sir.
Narayana sir has also joined. Good evening, sir.
Hello.
Hello,
Yes,
sir.
sir.
How are you?
Rajeev, nice to see you after a long time. Yeah. Great to see you.
So nice to see you, sir. So nice to see you.
Yes.
It's such a wonderful thing to see you. Wow.
Hello. Yeah. Hello, Priyank. How is life? Fine. Rajeev.
Yes, sir. Good evening, sir.
Narayana has also joined. Narayana.
Hello, Narayana sir. How are you?
Your audio is mute, Narayana.
Yeah, I'm sharing. My screen is visible, right?
Yeah.
Okay. Yeah. Once you let me tell me, I will start, because when I put my screen, I am not able to see the folks. So, thank you.
So, Rajeev, where are you now?
Sir, I'm in New Jersey, sir.
New Jersey.
I'm in New Jersey.
Okay.
Yes, sir. And it's been now 19 years, I mean, in the US.
Yeah.
How time flies, sir.
That's right. Great.
I got your number from VV Rao, so maybe I'll call you sometime.
Okay, you will call. Yeah, correct. We will.
Okay.
Narayana, nice to see you, Narayana. Oh, you're not able to hear you. Yeah.
Narayana sir, you are not audible.
You have to call him on telephone, I think.
Just a minute.
So, Rajeev, you're still working on your rocket motors?
No, sir. Now I'm not working on my rocket motor. Now I'm on. I've moved into the field of artificial intelligence, but across different industries. But when Dr. Priyank talked about this series, I said, okay, I think it's a good idea to share the experience in 95, 96, because it was a very different period. Now, of course, so many things have changed.
Okay. Good. That's a great field, artificial intelligence.
Yes, sir. It's been now many years now. Yes.
Actually, many years in the field, huh? But that field is getting very, very matured,
Yes, and interesting, matured, challenging, all at the same time.
I read an interesting piece of news today that most of the people who become rich this year, they are from artificial intelligence, AI. I think, Rajeev, you are also in that list.
No, you're being very kind, sir. I'm not in that list.
Yeah.
Dr. Priyank, I think we are on time. So if you want to start, up to you. Or you want to? Okay, your decision. Absolutely.
Narayana, you are able to hear? But you are not able to hear you, I think.
I think something is wrong with his microphone. Maybe he's on mute.
Yeah.
Sir, please unmute yourself. Narayana, sir.
You have to call him on phone, you know. Let me see if I can call him.
Okay.
Hello. Narayana, I can hear you, but you have to unmute yourself, you know. Yeah. Your maybe your sound in the you see the bottom right. Your sound maybe unmuted there on the laptop.
No, it is unmute also, still sound is not coming.
Yeah. Microphone, your laptop microphone you have to see. There you turn it. Yeah, bottom right. Okay, right. Right, yes. Okay, I think.
Yes, please. Yes, please. Yes, please. Yeah. Yeah. Thank you, Dr. Priyank. I hope I'm very much audible.
Yes, sir, you're audible.
Yeah, good.
Okay. Yeah, it's a privilege to be here, and thank you. I would like to thank the department for remembering me and giving me this opportunity to deliver this talk right after my esteemed, revered mentor Chakravarti sir, who's on the call. I cannot tell you how overwhelmed and delighted I am to speak to him after so many years, and also very much my senior Shri Narayanaji, who's also on the call, and it's a lovely feeling to be amongst the alumni. I thought it would be a good idea because I've been out of the rocket engineering field for many years now, but many people should know that the large, the ICBM class, IRBM class rocket systems, especially the solid rocket motor cases, it was an epoch in itself. And I thought it would be a good idea to share some of the experiences at that time. Now, as you can imagine, I will probably not be giving out many of the actual details, either of the systems or for reasons as you can best understand. But I will try to share the physics of wherever the challenges we faced in terms of many of the areas of a large rocket motor case design. And I'm talking in this case for a 2-meter diameter system. Now, it was an interesting period, interesting period because, it was a technology denial period. Even if you wanted to buy a tensile testing machine, DRDO had to provide an end user certificate. And I'm now sitting in a place from where the technology control regime started. And but this technology denial also was instrumental when in Dr. Kalam that time our scientific advisor to RM, he was also instrumental in doing stuff internally so that we handle the technology denial as an error. And at that time, we had already proven the technology re-entry system for Agni, which was a big deal in itself. And the 2-stage Agni had the first stage as a liquid system, the upper stage, the Daisy 2 system, as it used to be called. These were 1-meter systems. And, the major part of re-entry was already proven. And there was all the capabilities in the scientist community to handle the next big thing. A lot of things are unclassified now. So this was more about 3,000 to 3,500 kilometer range system to handle India's strategic needs. Now, when I joined, I had come from the army on deputation, and thanks to Dr. Chakravarti, who was really instrumental. I still remember him taking me to Lieutenant General Sundaram at that time, asking me that I should be put in the solid propulsion division to work on his system. He was leading a very prestigious program at that time for India's underwater ballistic missiles program, which was very prestigious. And I cannot thank him enough for that opportunity. And I was, after a long time, I was one of the few Army officers posted into the solid propulsion division of DRDL at that time. And and that is where I started the work somewhere around 95, 96 on the design of 2-meter systems. In fact, it was during the PDR, preliminary design review for Dr. Chakravarti's systems, that I was then at that time asked if I would be interested in designing this 2-meter system. As you can see, I was a young captain and a young, about to be major at that time, and it was quite an honor. Now, it is important, when you start working on a system you don't realize immediately at that time, I had not immediately realized the real complexity around designing the motor case for 2-meter diameter system for stage 1 and stage 2. And very soon I realized that a large solid rocket motor is an integrated system because it is case bonded. The propellant is cast in situ in the rocket motor case and of a very large diameter and large length and L by D ratios. In itself, it's a system. There is the casing design for sure. If you look at the and you know and each of these pieces of the integrated large solid rocket motor, the inputs come from mission level studies. It comes from subsystem level specification generation. So, for example, if you want to design a motor casing, then the system studies and the propellant studies a priori will tell you, what kind of operating pressures, combustion pressures, the metal thickness has to be designed for, what will be the fabrication processes. So if you look at this diagram, what I'm trying to show is the rocket motor casing is basically the crucible, and in which there are so many pieces that come together. And there is a rocket motor liner design. You need to look at the fabrication tooling and fixture design. You need to look at the bolted joint. And, in this case, there was segment joint because, for handling and the propellant casting, the L by D ratio of the system was very critical because the grain debonding, because these are case bonded systems, they're casted in situ. So, you can't have beyond a certain L by D ratios. Otherwise, you will face debonding of the solid propellant grain. And then you need a very elaborate propellant grain casting plan, including the safety plan. And many of the things were new, not for the country. Remember, Vikram Sarabhai Space Center had, the PSLV technology and the GSLV technology. But India, as a strong, democratic, and a transparent country with a very matured bureaucracy and a scientific community, our space program and our defense program were very distinct and did not kind of eat into one another, which is why we were respected in the international community. So for DRDO, this was a very interesting time when it was embarking on its own to design and develop the long-range system using a 2-meter diameter metallic systems at the time. Mind you, this is 95, 96, 97, 98. A lot of things, DRDO is a far more robust system to program today. I'm in touch with many of the scientists, and many changes have gone through. This Agni-III is now also a composite rocket motor. I believe stage 1 was still a metallic, the one that I had designed, but stage 2 is composite, and I think even they've tested the stage 1 solid rocket motor also with composite systems. There are many other pieces that you need to do. You need to carry out a viscoelastic stress analysis of the propellant grain. You need to design the flex nozzle systems for a very long duration without giving you the exact burn times, because I don't think in a public forum it's the right thing to do. But it was fairly long. Anything more than 80 seconds for a stage 1 solid rocket booster is a long burn time. And and then you need an integrated flex nozzle design, which is bolted to the nozzle end flange of the stage 1 and stage 2 systems. And then we also had to conduct the burst pressure and approved pressure testing of the large rocket motors. And even before you come to that stage, in the design and development phase, all the raw material QA specifications and acceptance criteria had to be accounted for. And then you need to build the specification for the test article review board. We used to call it TARB. I'm sure things would have changed, and they may be calling it something else now. And then, of course, all the environmental tests, the vibration tests, and other tests that were needed. And at that time, I was using finite element stress analysis software called ANSYS. And some of the code I had written was in C and C++. I mean, it sounds a small pieces of code for different aspects of motor case design. So, as you can imagine, I'm also trying to play on my memory, from nearly 30 years ago. And this is more about my experiences. This talk is not the Defense Research and Development Organization's capabilities today. They are far more robust and far more too many. But this was as a young rocket motor designer, a propulsion engineer, designing, using ultra high strength steels and trying to design the stage 1 and the stage 2 rocket motors and the retro rocket motors for the 2-meter system. Before I go, are there any questions? It's okay to make this interactive. Are there any questions at this stage before I go ahead and share more experiences? Okay. Now, the first thing, it was interesting that, the design approach ultimately for a metal structure, this is a very simplistic drawing, as you can imagine. I definitely cannot put any pictures of the system of that time. The system studies had generated the total impulse profile, the thrust profile, and the propellant system was already decided because this was the capability at the national level. And it was, of course, an STPB AP aluminum metallized composite solid propellant. The aluminum not only improves the energetics, but also fights combustion instability. And in fact, that was a solid rocket motor combustion instability was one of my very dear areas to me. And if I would have ever pursued a PhD, probably that would be an area, to pursue my PhD. But of course, I did not take that path. Now, as you can imagine, it was, I was surprised that I still remembered most of these equations, and to my pleasant surprise. And that can tell you that how deeply etched this profession is in my heart, even today. And everything that I do at this level of systems, subsystems, the thinking, the aerospace way of thinking of a large-scale integrated systems built with subsystems, and the systems thinking and systems design is very much part of my thinking process, which is why I could succeed in my alternate profession in mathematical modeling and AI and software development and building large digital platforms. Now, there were many guidelines from NASA handbooks, but these are handbooks and these are only guidelines. You cannot take them as gospel truth. You have to conduct experiments. So the maximum expected, and as a metal case designer, I needed the maximum expected operating pressure, and then based on certain standards, I would have to choose the proof pressure for which the rocket motor has to be tested as well. Now, the maximum expected operating pressure comes from the energetics of the grain and comes from the burn rates, and also comes from running at that time, because I remember I'm taking you back to the period of 95 to 98 and around that time. So Monte Carlo simulation is what I had used to find out what are the different plus minus 6 sigma deviations, standard deviations in the variation of burn rates, variation of propellant A value, and variation of temperature bands, for which this, again, I will not be sharing the temperature bands for which the system was designed. Because again, I'm not sure how much of things are declassified. And but once the maximum expecting operating pressure, which was at that time 60 KSC, kilogram per centimeter square, then based on the standards, the casing design criteria was designed, and the material selection criteria was kind of designed. Now, it was important. Let me go to this slide. uh, it is important. There were a handful of materials at that time. Certain materials were not available in India. And 15CD6, which was one of the materials used for the earlier upper stage Agni system, second stage of Agni in the technology demonstrator, was really not the right material for this large system because of the thicknesses that would be needed and then the fabrication challenges. And I must point out, for a young material, for a young propulsion system designer, I had to think many things a priori. A lot of interactions with different departments. I remember Mr. Damodaran from the design engineering team. I remember when I took my drawings to him and I put the tolerance at 2 meter diameter, ovality of 4 millimeter for the cylindrical shell. He just threw the drawing. He was laughing. He's saying, do you even know, you're violating the physics of fabrication. And it was a learning curve for all of us. And I think as scientists, one thing I still very fondly remember is the humility, our humility to learn, our ability to, say, I don't know. And, and our ability to talk to our professors at IIT Madras, our colleagues at DMRL. I remember Professor Ramarao and Dr. Malkondeya from DMRL who are working on a very similar steel like Maraging steel, but low alloy. Maraging steel that is mentioned here is an ultra high strength steel, but at a very high alloying element of nickel and cobalt. And these alloying elements are very expensive. Many times we don't appreciate these small things when you start designing a rocket motor. You think it's all about putting some equations together and arriving at a thickness. That is the easiest part to do. The stream of events that started from that thickness was just mind-blowing, mind-boggling. At the national level, where would we get the forgings? What part of the rocket would be a forging? What part of the rocket would be formed from a sheet? What is a sheet? What is a plate? And how do you even make a sheet of this dimension, which can be rolled into a 2 meters of diameter? Again, I'm not going to give out sheet dimensions and the forging thickness, forging inner diameter, outer diameter, and height of the forging for reasons as you can appreciate. But I still remember those dimensions so fondly. There were 10 different sizes of forgings. And out of 10, at least I remember 8 out of my memory, even today, after 30 years. And it was not easy. What should be the OD, outer diameter of the forging? What should be the inner diameter of the forging? Because the outer diameter and inner diameter and the height of the length of the height of the forging depended on the national capability in India to build such a raw material, forms. That itself was such a large dialogue at that time. And DRDO, remember, was doing this on its own as Department of Defense in the national interest. And for me as a young scientist, sitting with all the seniors, Dr. Chakravarti is already a program director at that time and leading a very prestigious program. And to sit with these gentlemen was, and so much of learning. I would imagine as a young scientist, when I used to hear them talk about, area ratios and combustion pressures and tolerances, and they were so well informed and they were so knowledgeable that for me as a young scientist, every day, even if sitting in one review meeting was an education in itself. And that again brings me to the point that I cannot even express my happiness that Dr. Chakravarti is today on the call listening, and I'm overwhelmed that I'm presenting to him something that I learned from him. Yeah. So, and the third material was 6AL4V class, right? Again, DMRL was the one making this. I remember Dr. Banerjee was the director of DMRL at that time. And I was meeting him, and he was so pleased that DRDO was considering. He was a titanium alloy expert himself. And he was so happy, and he sat with me and gave me all the material strengths, the ultimate tensile strength and the yield strengths, which were actually achievable. And especially when you talk about very ultra high strength steels, fracture toughness becomes very important. And for Maraging steel, a 90 MPa root meter, is a very good fracture toughness. And many of you probably may not have an appreciation for fracture toughness, but for a strength of this nature, 1750 MPa root meter, or this in kg per millimeter square, 90 MPa root meter is mind-blowing. And this fracture toughness and this strength does not come from carbon, mind you. Many of the steels, carbon also gives you a lot of strength. In this case, it comes from the different molybdenum and cobalt microstructure of margin steel, which happens when you age the system. And as a designer, as I said, you need to know these things. And I cannot tell you how much I learned from the fabrication agency. I think this part may not be classified, but at that time, Walchandnagar Industries and L&T, these were some of the few companies that were, had the reputation of being able to handle such, manufacturing of such systems at such scale. But even they, had limited experience at 2 meters. They see every diameter. Just because you have experience at 2.5 or 3 meters doesn't mean exactly things will work the same way at a 2 meter scale, because tolerance and ovality correction and machining tolerances and forming tolerances, perpendicularity, all these things, how do you weld a forging and a sheet, and what happens to the deformation, what kind of tools and fixtures. I cannot tell you that there were such humorous incidences. As a young person, when I joined DRDO, somebody said margin steel was in solution annealed state. And I was scratching my head. I said, solution annealed. And I was thinking, probably margin steel must be coming in liquid form in drums, and because I was not a material scientist, but it's a learning curve. And firstly, I had to remember verbatim all the data on my tip of my fingers for every strength of 15 CDV6 margin steel, Ti6Al4V, other forms of steel, other forms of aluminum alloys which were weldable like He20 and so on. And these had to be on my fingertips. I never had the luxury of referring to books all the time in a review meeting. And in my first 15, 20 days, the first thing I did was understood all the fracture toughnesses. I would go to DMRL. I would understand stress corrosion cracking. I would speak with Dr. Kamath. Dr. Kamath and I used to be very good friends. And, he was also a young scientist. And, we spent days together. I remember we have a joint paper together on stress corrosion cracking and fracture toughness for ultra high strength margin steel and silicon steel, which was a DMRL 1700 steel designed, built by Dr. Professor Ramarao and his team under Dr. Malkondeya and Dr. Kamath at that time. And I still remember Dr. Kamath and I published a paper at that time on stress corrosion cracking. And we had created welded samples and left them at Mandapam camp, which is the world's most corrosive, second most corrosive environment in the world after Panama Canal. Even these things I had not known. Right. And so we had to do a strength-based design, and I had to do the check for fracture-based design using the fracture toughness. An important consideration was the sheet thicknesses and plates and forgings, and how much forging tolerance. Remember, we had no experience. Mr. Damodar and I had made countless trips to Walchandnagar Industries and other places. The complexity of the tooling and the forming of the domes of the rocket motor, we had used torus spherical domes. The material for the fasteners, the size of the bolts. In this case, we were looking at M16, M20 kind of fasteners. And these were fine-pitched fasteners. Fine-pitched fasteners at that level of sizes pose their own problem. And then you had to use materials like Loctite to, even before you start tightening the bolts and how do you decide the torque for these fasteners? Remember, NASA handbooks will not give you so many details. And we were under a technology denial regime. Everything had to be done indigenously. How do you even design the segment joints? I remember conducting discontinuity stress analysis, for many of these pieces. And, doing a discontinuity stress analysis for the wiring portion, for the end domes, deciding the design criteria. As you know that, 60 KSC was the maximum expected operating pressure. And the proof pressure, that this was the pressure at which the rocket should always be sustainably tested after the first burst test. So I remember predicting the burst test between 99 KSC to 107 KSC. And the rocket motor burst at 106.7 KSC. And I still fondly remember my mentor, Dr. Agarwal, R.N. Agarwal, who was the program director of the program, came and literally hugged me in Walchand Nagar, because it was very close to the burst pressure that we had predicted. And I was also scratching my head that, yes, I had predicted the burst pressure, but beyond a certain level, you want God's grace for your scientific, scientific predictions to work. And, so it was a mix of faith and scientific temperament and scientific maturity. And the faith in God that, oh God, I had butterflies in my stomach as we kept on increasing the pressure in the oil was used to test. And this massive, bolted joint of stage 1 rocket motor, it was quite a big size, and at 2-meter diameter, it was a formidable experience to go into the pit, put all the strain gauges, and design the pressure. And there were many new things for us, like the term biaxial gain was very new, especially if you look at the pressure, there is a longitudinal stress, there is a hoop stress, and there is a radial stress. The radial stress is very small, which is the pressure itself. In kilogram per millimeter square, the pressure is the radial stress, which is very small compared to the PR by T, which is the hoop stress, and PR by 2T, which is the longitudinal stress. So this is basically, you can ignore the third state of stress, which is the pressure, compared to the amount of stress, which is the longitudinal stress and the hoop stress. Which is why in a large cylindrical thin shell, it is called a biaxial state of stress. And because of the biaxial state of stress, the actual UTS is not the ultimate tensile strength, is not the real strength. You get about 12% gain in the tensile strength. And this has to be experimentally denied, but theoretically the gain is up to 15%, and you can actually derive it. And I had actually derived that formula just because I wanted to be very clear that what I'm doing is correct. So, but we used 12% at that time as biaxial gain, and that was kind of gave you some benefits on the allowable strength of the material. And based on certain NASA standards, remember, there was so much of argument on the safety standards because the weight of the system, remember, it is just not arriving at the thickness. The weight of the system is a system constraint. And the range of the system, especially for the upper stage, the weight of the upper stage is very sensitive to the overall long range, the range of the system. And there was so much of argument around using 1.33 on UTS, 1.25 on yield, or 1.25 on UTS and 1.125 on yield. And Dr. B.S. Sharma at that time, he was leading the structures division, Mr. Kaushik. These were, our leaders and gurus, and, they had so many disagreements on, that 1.25 is not even a thing. We have never designed something like this. This is a mission critical system. But then we chose these lower factors of safety because, number one, there was absolute confidence in the propellant energetics, and there was absolute confidence on the maximum expected operating pressure and its predictability. The burn rates of the propellant grain, there was a lot of confidence around the burn rate achievability at HEMRL for the propellant grain for that class of, it was a bimodal ammonium perchlorate. Again, I cannot give you the particle size, but many of the people on the call are aware of those data points. And, again, I will not give you the propellant composition of percentage of AP, HTPB, and aluminum. But again, these were standard, and the country had immense knowledge of that. So the propellant expected pressures were very well predictable. There was a handle on the material parameter. Now, I will not give you many details around where did we get the material from, who helped us to get the material, where did we do the forming and rolling. But the rolling and forming, this capability at 2 meters was developed within the country. I remember Dr. R.N. Agarwal funding Midhani for building an electronic furnace. The material of marging steel had is supplied in lower strength solution and in form when the hardness of the material is around 34 HRC, 34 HRC max. I'm even surprised that I remember this number. But once you do the aging at around 485 degrees centigrade, the hardness of the material goes to around 58 HRC, 55 HRC. You can't even do machining at that. The tools will break at that hardness level. So the rocket motor machining for the forgings and for the edges all had to be done in the solution and in form as close to the final form. And then after aging, the final machining is very limited. Maybe I just can't give those numbers, but very less. So all these things had to be understood. The weld efficiencies had to be understood. The design weld efficiencies were 90%, but we actually achieved more than 93 to 95%, in some cases 98%. The weld mismatch factors are very critical. When you weld a sheet, a plate or a sheet to a big thick forging in the wiring sections and the igniter boss sections, nozzle and flange boss sections, you have large bending stresses because of the mismatches of the welds, and even the sheet, this under pressure deforms as much as, again, sorry, I can't, you can calculate it for some who understand, but quite a lot, and the deformation, imagine this becomes like a balloon in the centers, wherever there's the internal pressure. And the forgings are heavy, so they will keep it down. So there is a large bending stresses in the wiring area and in the igniter boss and the dome welding area in the bottom, what you see here, the joints that I've shown. This is a big forging. So you need to allow for those higher stresses. One thing was that when the domes at those days were made with a forming process, which was a very well-defined process by Valchandnagar Industries and other larger players. And the dome, when you form them from a starting thickness, they become thin. There is called thinning of the dome, especially towards the igniter boss area. And we had to cater for that. Now, our sheet thickness for the shell and the sheet for the domes were the same thickness. Now, we accounted for the thinning of the sheet at the dome during the fabrication and forming, but it did not actually thin that much. And so we landed off with a very large weight, which was not even designed. The design thickness of the dome was at some level, and I had more than 10% extra thickness, which was absolutely not tolerable. I remember getting such a scolding from Dr. R.N. Agarwal that, how the hell did you not even think about it? And quite honestly, I had not. I mean, I assumed that the material will thin by that dimension based on the fabrication details. It did not. So then we started polishing the plates for the domes to a lower thickness because, the thickness of the sheets and plates was standardized. So we would get a particular thickness for the whole system for economies of scale. And then the sheets for the domes were identified and we would polish them to a lower thickness before they were actually used for making the domes, torus spherical domes. And this also added cost. This added fabrication time. And all this was important. And remember, time to market was important. So every day, Dr. Agarwal was asking me, what is going on? When is the first rocket ready for burst test? And, it was amazing. I cannot tell you the pride, the Josh was just mind blowing. I cannot even tell you. I still gives me goosebumps. And then designing the system with all these pieces came when the first rocket motor was ready and we decided to do the burst pressure. Imagine the amount of oil we had to put in the system, even for pumping of the oil, putting of the strain gauges. There were more than 100 locations for strain gauging on the dome, on the cylindrical shell, on the weldment area between the forgings and the sheets, and certain critical areas of the longitudinal weld seams. And the number of weldments was mind-blowing. And our fabrication processes introduced more welds. And we could not have large shells because of the L/D ratio of the propellant grain limitations because of the debonding. As I said, it is not about thickness. A solid rocket motor case bonded system is an integrated system in itself. And you cannot design it in isolation. Every nut and bolt, when I was designing the pre-torque to be given, the calculation for the torques, the calculation for the friction factor on the torque, the calculation for the cadmium plating bolts. And then somebody would say, oh, if you do cadmium plating and then there is hydrogen embrittlement, and then how do you handle hydrogen embrittlement? And mind you, we were doing this for the first time, so many things. I still remember the TAR review when we had to go to TAR for the burst test. And I cannot mention where did we conduct the burst test, but it was just mind blowing, And when the rocket motor actually was tested, the first statics test where Dr. Kalam was there, and I'm sure many of the folks here, my seniors were there when the rocket was static tested. And many things happened during that static test. Stage 1, as I said, burns for a long time. Stage 2 burns for a long time. Stage 1 had a star configuration propellant grain with a tubular propellant grain. And that itself was a technology in itself with a segment joint to have that kind of a structure. In stage 1 itself, we had 2 different propellant configurations to define the mission requirements. And then stage 2 was a tubular system. It was quite an experience, right? And in summary, we used the classical pressure vessel-based design, which was not the end of the thing, because I had to check for fracture-based design, where I had to do so many sample tests, build the corrosion protection. Mind you, these systems were all nuclear capable, and you would always pray that you never use these systems. But this was for the defense of the nation. And so you had to store these systems for 15 years, 20 years. So we had to design coatings based on stress corrosion cracking studies at Mandapam. And I know from Dr. Kamath, that these were there for 15 years. And the coatings which was developed at CRI Karekudi, they had built those corrosion protection systems. And then, we had the unwelded samples, welded samples, plain samples, kept at Mandapam camp. And they did very well. And bolted joint segment design, I had conducted an axisymmetric bolted joint design, which was, of course, questioned because bolted joint cannot be an axisymmetric system. So I had to again conduct a 3D sector analysis. Those days, ANSYS 4.3 version had so many limitations. We had compute problems, storage problems of data. To do a full 3D was not even possible. My model would hang. My element size, what kind of elements, my modeling. I was learning finite element analysis. Remember, I had come from the army, and I had to learn. I used to open the CAD camp center at 6:30 in the morning, collect the keys from the security, and then open and sit with those manuals. They were yellow-colored, thick manuals. It was not, the documentation was not built in online in the software system the way it is today. I had to open those manuals, keep them on my lap, and then learn how to do an axisymmetric modeling, a 3D modeling. And there was a viscoelastic material of the nozzle in the flex nozzle. How to do? I had to learn about Mooney-Rivlin coefficients for rubber, and everything was learning. Nothing was done everything was being done for the first time, and there was so much of help from so many different national level laboratories who collaborated. So much of input from so many places. And the only reason we were successful was because of our humility and the ability to learn, the ability to say, I don't know, which I think are all leadership qualities. The leadership of Dr. Agarwal, the leadership of so many people, that my memory fails me. Dr. Kalam himself was at the forefront of on the system that he was so, was interested in. Dr. Chakravarti himself was leading a very large rocket motor program of a substantial diameter, where buckling analysis was a very important piece. And I had carried out theoretical buckling analysis, when I was in solid propulsion division. And it was what I learned in his program. that was, that made me capable to design the 2-meter diameter Agni-III system, stage 1, stage 2, and the retro rocket motor. The retro rocket motor at 1.75 seconds was another challenge. And I had to design it using a double base NCNG system, which again, HEMRL at that time had a very well-proven propellant system. And I designed the retro rocket motor. I believe the retro rockets, the stage 1, they are still the same. Everything, the design is the same, which to me is a matter of great pride and privilege. That even the QA documents I had to write along with Mr. Karandikar and Mr. Bhattacharjee, Dr. Soni. And I remember these names so fondly. We used to have arguments and disagreements, but it was so much fun and it was so much full of respect that I just, I am getting emotional here as I remember those names. Dr. B.A. Sharma, I had an argument with him and I had to meet him in Pune, where he would disagree with the FEM results. And then there was Dr. Acharya who kind of presided. Dr. Agrawal arranged that meeting and we met in Pune. And finally we agreed on the thicknesses. But these are people, the names I take with so much of respect. Mr. Kaushik, Dr. B.A. Sharma and Chakravarti sir who's on the call. Without these stalwarts, on the shoulders of these great people, stood the future of DRDO and the missile program where it is today. Without their efforts, and they took a bet on us, on youngsters like me. I used to sit in such senior meetings presenting to the Director General of Military Operations. I was a young major, Indian Army is the 3rd largest army in the world. A young major sitting in these review meetings, and the kind of respect I got, the kind of respect I was given, unbelievable, So, yeah, with this, I would say that, I end my call and I would stop presenting. And I would say that if there are questions, I would be more than happy to take. Yeah.
Yeah, the floor is open for questions now.
Again, I have to hold many details, as you can respectfully understand. But I'm surprised I remember all these after 30 years. But yes, they are a part of me. Yeah. And I would fail in my duty if I don't thank my teachers at BIT Mess, Dr. A.K. Chatterjee, who was my dean and who was a dean, my advisor, thesis advisor, Dr. Munjal, Dr. Joshi, Dr. Mohan Verma. He was a young man himself living in our hostel 5. And, it was amazing. Those days was just amazing. And my teachers were amazing. So my humble gratefulness to all my teachers at BIT Mesra. And I visited the campus after 34 years in month of December. And with my wife, who's also from BIT Mesra, Alpana. She's from the computer science department. And I met Dr. Priyank, I met Professor Biswas, Professor Rajeev. And it was a very emotional moment. So I'm so delighted to give this talk right after Dr. Chakravarti's talk. So thank you, sir. My humble respects to you. And yeah. Over to you. Over to everybody.
Sir, actually, what I learned, actually, you have discussed so much about 2 meters diameter, solid rocket, all that. From your learning, what we understood is that whatever we do here, it is just a small rocket where we don't even do anything actually. Like you have said, forging, welding, we know all the information which is required. If you see here, you must have seen our lab, right? We are doing solid rocket, liquid, all heavy rocket. Like you said, nut bolt, how much we do the tightening, how much twist we should give, torque, all that calculation, all that is required there. In that respect, actually, you have discussed about so much complexity, all that is there in that large rocket. In that way,
no, but I'll tell you, as a young scientist, everything, what cannot be taught in an institution is curiosity and passion. right? This nobody can teach you, right? You need to be able to say, I don't know, and go and ask. You need to go to and read. You need to, so, but, I think the problem solving mind, I learned so many things on the job. So I think what the department, what I like the foundations of burn rate variations, the foundations of using the right kind of catalyst, the understanding of metallization of propellants, the understanding of D-bonds, liner design, the understanding of thermal heat transfers, the understanding of instability. This is important as a young designer. And then when you learn through interactions. When I talk to Dr. Damodaran on fabrication, when I talk to the HEMRL people on burn rate possibilities, the A value in the burn rate equation, the N value of the stability exponent, you learn, and you need to know that that is how you become a real scientist after 20 years. The real competency, the unconscious, what I am able to tell you right now out of my memory, even after 30 years, comes from those intense arguments, intense disagreements, intense review meetings, listening to your elders. I think it's a combination. A young scientist is shaped by so many challenges. I'll tell you that the technology denial regime was the biggest reason for our nation building at that time. And Dr. Chakravarti, who was a leader himself at that time, will agree with that. Mr. Narayana, who was part of the space program, will agree with that, that is how nations are built. So I would thank, yes, our lab is small, but even colleges always have small labs. But colleges train students which become larger than life. MIT Crumpet is still very small. It created Dr. Kalam. BIT lab is still very small. It created Mr. Narayana and Dr. Chakravarti, right? So don't underestimate the power of that small lab. It is a temple.
One more question, like in real rocket, like a nozzle itself, if we see complex nozzle, there is a O-ring, arrangement, sealant, all that. If we start understanding, that is a complex part itself. Like we do just a convergent divergent, we make 15-degree angle and all, just we do the rocket testing. My question is like fabrication of all complex, it is within the DRDL or it is from outside? How, like we are not able to do some simple fabrication also. How is that done?
So Dr. Rajeev, I think I cannot name many institutions, but it's a military industrial missile complex. There was a term, right? Military, see, when you build systems like what Dr. Chakravarti built, what DRDO Agni program is, these are part of national capabilities. These are not simple things. So you need a military industrial missile complex. So many small industries came up in Bombay, in Hyderabad, for making the O-rings, for example, O-rings. So many industries up from where we could get Loctite 242, right? To so many small industries where we made these bolts, and it's a national competence, which is why as I said, even to get a tensile system testing machine, DRDO could not get it. We had to give an end user certificate. So our research laboratories used to get that certificate. DMRL had. So, we had to manage it as a country. So, yes, these things are complex, but I tell you, everything I'm presenting to you was perfected in 95, 97. And Mr. Parthasarthi was heading the fabrication in Valchand Nagar. I mean, I met him in US many times. His family is here. We have great capabilities now. So I think sometimes what happens, Dr. Rajeev, is when you are in a college environment, thoda sa you feel that our labs are small. But I'll tell you, the moment you put these scientists in a big lab like DRDO lab, which is why I would recommend internships, training, inviting scientists from the labs to give lectures, partnerships. There is no shortcut. You need to invite people to give talks. Like many people who retire, my batchmates, like Mahapatra retired from ADA. He was one of the leading structural scientists at ADA, right? So use people like me, use people like Dr. Chatterjee, Mr. Nara, Dr. Narayana. Nobody can stop the department, right? So, like I cannot give many details here on the public forum like this, but in a department with a chalk piece, I can talk so many things, right? And that is how you learn, right? No matter how much I care, I want to tell you what is the propellant composition. I want to tell you the bolt torque. I want to tell you the bolt size, but I can't. And it's not correct. It's our national property. I have no right to do that. But in a chalk piece in hand with a student in front, it's a very different feeling. So my request would be to invite people, interact more, create internships, and then work the way through.
Yes. Thank you, sir. We learned so much. Even students who are there, they might have understood the difference between what we learn in the simple geometry and how the real system looks.
But remember, we still study steady state, solid rocket ballistics. We don't study unsteady solid rocket motor. The solid rocket motor, the nozzle throat, is designed for stable combustion. Remember, the combustion in the rocket motor is not detonation, right? It is combustion, stable combustion, right? So I don't use unsteady combustion. So remember, there is a lot of value in studying steady state combustion, while you must understand the combustion instability. We still assume perfect gas equations, right? Well, the reality is the gas is not perfect, but the variation between perfect gas and imperfect gas is 5-7%. But the whole design is based on steady state combustion, and you design the throat diameter to ensure the steady state combustion. The whole equation, that chamber pressure equation, comes from steady state combustion. So, आप परेशान मत होइए इसको लेके.
One more question is that you discuss one equations, thrust coefficient, CF. You get CF equals to CF naught plus area ratio in a function of pressure.
Yeah.
Can you tell a little bit about what is CF naught and that function?
Oh boy. Okay. So area ratio. The propellant has a specific impulse, right? And the propellant has, from what I remember, I'm an AI engineer now.
No, normally we teach just CF naught, which is a thrust coefficient.
No. So the pressure ratio, the P by PC. Remember, as the rocket keeps going up, the pressure keeps falling in the ambient pressure, right? So the area ratio and the C star and ISP, these are related. The specific impulse of the moment you select the propellant, your C star is fixed. The characteristic energetics is fixed. How much of energetics impulse you can draw from that C star is your ISP, and depends on an area ratio. If you allow the gases to expand, you can get the exit pressure can be close to ambient, but you never want the exit pressure. P is never equal to PA. It is slightly always underexpanded. Yeah. So P is always high. So these are the pieces, and this is, I think, available in Sutton, the CF naught and the available. It is available. And if there is a handbook, volume 90. Of course, now 30 years ago, that was a very new volume. It was a blue book, Solid Propellant Handbook, volume 90. You should probably look at that.
Okay, thanks.
I'm surprised. I remember the volume also. I'm just surprised.
That is what I understood. You are so fluent in remembering and telling all the names. Otherwise, we'll take normally some name we'll remember, then we tell. And you are so easily remember.
He was actually very much dedicated into the system. That's what made him remember this much.
Yes.
But ours is academic lab, and we cannot scale up to a very largest extent because the statutory compliances and all will become more important, and we'll have to go for many safety measures and all those licenses and all. right? So anyway, smaller is better as of now.
No, no.
Definitely we're gonna grow.
My question was not a smaller. We are saying just let us say we tell the student go and do this flange welding.
Absolutely, they need to
Nobody
learn those
cares.
design, the machine
Nobody
designs,
cares that
especially.
how much is the
Ah,
strength of that welding.
right.
They
I
should
will
they
just
should do
say
the design
fix.
first of all. This is what our
We
students
say
actually
just
used to
fix
do.
the nut bolt. Nobody knows how much
Um,
tightening you should do. Nobody just pass out. They don't know how much bolt required for that flange fixing.
yes.
All that what I wanted to
Right.
tell. Not
That's
the
what I mean. A bit
small.
of machine design is required. That's where the mechanical engineers play the role.
I think in my view, see, I learned a lot of things in DRDL at that time. I learned combustion modeling, programming. My feeling is in the department today, software is so much part of the design process. We should stress on machine design. We should stress on combustion, the internal ballistics of rockets. We should stress on fabrication processes. We should stress on computer programming in Python and certain capabilities. Will be very helpful when they join DRDO and ISRO. And these young boys and women are very smart now. They are, I'm sure but they attend the hackathons, they attend all these. And I know Dr. Priyank, you organize so many things. So I'm very happy to see department is very active. But I would like to hear, my seniors are on the call, so I should, Indian culture is all about respect to the teachers and gurus, So Dr. Chatterjee and Dr. Narayana, please, over to you. Yeah.
Sir, you're on
You're
mute.
on mute,
Check.
sir. You're on mute.
It was really a fascinating lecture, Rajeev. I really admire you. You remember so many things, so many details, as if you left DRDL last Friday evening. You have taken us back, myself and Narayana, to the memory lane, 30 years back. And you're so vivid, and you talked about so many of our colleagues. I'm really delighted. Dr. B.S. Sharma, Kaushik, Karandikar, you remember every bit of it. Dr. Aryan Agrawal, all kinds of things. And you're becoming a wonderful storyteller, I tell you. I saw you very smart, young, dynamic major DRDL. And now I can see you're a very, very matured professor and a storyteller. You explained this complex thing of air booster, managing steel and all, with all complexity so nicely, the whole kind of stories and all, and anecdotes and all. It is very humorous lecture you have given and a tough subject, a difficult subject, but you have done a wonderful job of 2 meter. That was, big thing for the DRDL, what you have done for the nation. And it has given the confidence of many people. If you visit DRDL now, you'll be very surprised and you'll be happy to see there are so many young people. They're doing this various types of propulsion system. The managing steel is still there. Managing steel is continuing. And then another thing has come, perhaps when you were there, it was there, but it's come in a big way. Now we are working on the carbon composite.
Yes.
And there's another big development of the flex nozzles, various divergence section, and all kinds of. It's a big way going on, and they're doing wonderful thing in DRDL. What are the foundation? You are one of the member to lay the foundation. I know you have seen you with a n number of times with my very close friend, Dr. Suvanand Rao.
Yes.
Must be remembering him, and is a wonderful talk. Though you are in different field, you are in the artificial intelligence and all, but you still remember every bit of it. But I must suggest that Rajeev and the department, you can keep contact with him. He is so knowledgeable. He can guide many students' projects, in this field. And your questions of, you are doing a simple thing. I still remember the hybrid propulsion rocket motor, what I got fabricated there and got the first firing, the aniline formaldehyde and RFNA, it's a wonderful, then the soil burner. It's a wonderful thing. I still remember doing the aniline formaldehyde, mixing aniline and formaldehyde and polish the grind it. And one day I poured RFNA on my fingers, still the scar is there. It's all very interesting what he's telling. It's a great temple. What he said is exactly is a great temple. But what I suggest, you take your students to DRDL Okay.
Visit.
And put them there for some time and let them see how they are working on the modeling steel, how they are doing different things, how they're doing the combustion instrument study, how they're doing the static firing. We mentioned about static firing, a big motor is something to watch, so much of instrumentation and so many things. So, Priyanka, I suggest that you can take some people who are studying propulsion to DRDL and see.
We'll plan, sir. We'll plan a visit to Hyderabad.
Very good. This interaction, Rajeev, what suggested is very interesting. I am so happy to see Narayana also here with us. Narayana, you are back in India, is it? Or you're still there?
You're on mute, sir. Narayana, sir, you're on mute.
Something you're...
I think there's some technical issues.
And thanks, Ali, for continuing with this program. I hope this program is continue.
Yes, sir. We will try our level best.
We will wait for this program, to see all you people.
No, but I want to mention one thing, Subhanandra was leading the department, solid propulsion, and Valchand Nagar would come and ask for deviation on some machining tolerance. And he was my boss, and he would ask me, Rajeev, how can we look at the design documents again and give the deviation waiver? He allowed, the empowerment of your senior scientist to guide you. Mr. Subhanand Rao, gave me so much of empowerment, right? That I could go on the phone and say, yes, waiver given verbally. When I come to the next time, I will sign the waiver papers. The faith of your leadership on young junior scientists and the whole machinery work, if Subhanand Rao Saab would have not trusted me and my design, we would have never achieved the speed. Imagine if I had to wait to go to fabrication and then give a waiver. We would have lost time. I cannot tell you the energy and the leadership of so many people that comes together to build a complex system which is our national pride. And even today, when I take these names, I meet Mr. Subhanandra every time that if I'm there, I'm so grateful. If Dr. Chakravarti would have not put me in SPD, I would not have designed that system. If I had not designed, worked on his program as a young man, and I remember he held my hand, took me from the library to meet General Sundaram, because I was from Mesra, and so these are the leaders on which we ride, and I think, and today my juniors who are scientists, these are now lab directors. It is such a good feeling, It's such a good feeling. So, yeah.
So we have a few people joining from outside BIT also are there. So if there are any questions from them.
Yeah. And my apologies, I held back all data points, but I hope you will pardon me, because I just cannot do that, right? I've not done that in 30 years, and they will go with me when I die. So nothing is going out. So
Dr. Shelley, few people are from outside, right? Yeah. Please. I think somebody has raised his hand. Just quickly. Yeah, Himanshu. You can please.
Good evening, sir. Yes. Yes, sir. Myself, Himanshu Karar. I am from SRM University, Chennai, and I am currently pursuing aerospace engineer second year. Yes, sir. So currently I am working with potassium nitrate and sugar fuel rocket for at least 2-3 years as a hobbyist. But as a enthusiast also, I want to follow my career in propulsion itself and make a change to cryogenic propulsion later. But currently we are working on solid propulsion only. Like we are in the college state only, so we have not much facilities here. Yeah, so sir, my main question was what kind of analysis and simulation and experiment, particular experiment we have to perform to get all the characteristics of propulsion, like propellant and all the dynamics.
So I think, there are many more knowledgeable people on the call on that, but, you need to carry out burn rate testing, strand burner testing, burn rate testing in small motors, build the characteristic of the burn rate variation with area ratios, create experimental data. You see, the Russians always had a lot of experimental data. So as a country, we need to, everything doesn't have to go back to the design board. We should create nomograms and experimental data. And HEMRL does a good job. So different propellant combinations, different levels of metallization, you can create the burn rate variations and standard burn rate at room temperature. So I think those things we can easily do. And you don't need full-scale testing. So most of the data, for example, from the Agni program or from the space program, can go back to the colleges. And the colleges now can have some data in an anonymized form without knowing where they are used. But you can know that the burn rates of this level at this area ratios are possible. At this, not area ratios, at this temperature band. The initial propellant temperature, the final. So all that,
Arush.
you know, but that is only possible
Arush.
when there is an industry, academia interaction. You know, that is needed. So that should not be, but there are standard methods. You don't have to redesign everything. There are standard techniques using which you can totally characterize the propellant fully, including the viscoelastic properties of the Mooney-Rivlin constants, which are used in the structural analysis of the case-bounded propellants.
I think Himanshu, time, I mean, if you have time, you can definitely visit to our BIT labs. You know, if you have time, you know, you can plan a visit to Ranchi, so that maybe if you wish, as an intern or anything, you'll be able to see the labs. You can be exposed to that. That's your choice.
Okay, sir, definitely. Thank you, sir, for giving the input.
Any other question from?
Even it is there in IIT Madras, you can approach. If you, for burn rate studies, they have Crawford bomb setup.
Same thing. We have also.
We also have all the lab facility.
Okay. Any other people from outside? If you have any queries, otherwise we can conclude.
Yes, sir, I have a question.
Oh yes, Parthoji. Yeah, Dr. Partho is the assistant professor in our department. I think Rajeev sir has already met, and he is a competition person. Mostly to CFD. Yeah.
So, you know, our batch was the first batch when CFD was introduced as a course by Professor Mishra, Dr. J.N. Mishra. So first batch when CFD was taught in BIT Mesra.
Sir, I work in a fluid actually, not that much in combustion or in structural that much. So I have just one simple question. You told about the factor of safety around that 1.125 something you told. For so that is it is not very small. What I think that generally we take for designer, it is generally taken more for safety purpose. Though it will increase the weight, that is also another concern. But generally, that much is generally designer is used for this rocket design, rocket casing design, factor of safety, whatever you told.
Yeah. So remember, the margin of safety, there is something called margin of safety. Margin of safety is 1 minus factor of safety, right?
Okay.
And in aerospace systems, these are not man-rated systems. These are one single shot systems. So the margin of safety can be very close to zero, but not zero. Because if it is very high, then your weight is very high, your mission will not be met, right? And the safety factor, discussion is a very complex discussion. It is a discussion of fabrication capability, propulsion characteristic, stability, weldment stability, fabrication process stability. After all that, these factors of stability, I think today, instead of designing on NASA standards, India should build India standards. We have enough capability in the country that we should use India aerospace standards for our systems so that we don't depend on many international agencies. Now, cooperation is always good, but capability building is important, right? So to answer your question, margin of safety should be as close to zero as possible. But remember, in the entire system, the factors of safety or the margins of safety are different because of the fabrication tolerances and processes. So, but what I gave you are the right ones.
Okay. Okay, thank you, sir.
Yeah, don't ask me more details, please. Yeah, I can't give you.
Yeah, so I hope, is there any more questions or? Okay, I think we can, now I will just have a brief on what we had today. And it was really an interesting talk by Rajeev Sharma sir. And he talked about the importance of not only materials, design, fabrication, the material compatibility, corrosion, everything has been collaborated. How every part is important for a motor design. It's starting from the design aspect to the material aspect to its fabrication, the lining which you are using. Everything plays a role, and this is giving us an idea that yes, no doubt we are doing on a very small scale, but we can also add on to some more this kind of thing so that we can improve on getting into a real system, real working system. And really it was really interesting to know about when it, but we think that it is a very simple thing, but yes, the simple is complex sometimes. So that is what the idea is, that everything we should take to our requirements of a mission plays the main important guiding criteria for design. And I think that takes us all around and that gives us all experiences. And really I thank sir for giving us so much of enlightenment and really encouraging us. And it is so nice that it is that we were able to have such a discussion on this platform. I thank everyone. I think there is one question from, okay, okay, it has been sorted out. So the as it was streamed already, so you'll get it on the online. Okay, from this, I would like to take. I'd like to thank every one of you for joining, and in this lecture series and giving us and interacting with us, giving us so much of encouragement. And I hope we will continue this and take this to a newer heights as far as possible. Yeah, and everybody is also writing this that it's been a very wonderful experience. I hope this experience can continue, and I thank for each one of you, our Zoom seniors and other people who have joined and are interested in learning more.
No, Dr. Biswas, you don't know Dr. Chakravarti, Mr. Narayana. These are all national treasures.
Definitely.
You may, just because they are on the call, we feel that it is, but these are our national treasures. These are,
definitely. They are not only our national treasures, they are our seniors. They are our not only our, they are our path guiders, I should say. So that we always look forward to them.
So, Dr. Chakravarti sir, me and my wife, we are returning to India. We will come back to India in 2025. We'll be settling in Bangalore. And
great news, huh?
Yes, sir. And I will be spending time in teaching and writing some books. I want to teach and write some books. So we and my wife will be returning to India and settling there. Yeah.
You're welcome to India. India is a different India now. And, I'm so happy that you will be again with us. And
yes,
I'm sure you'll have more interaction. And,
yes, sir.
Very nice. It's a good
so
news.
Hope to see all of you again in the BIT campus and have an interaction.
Yes, so let me tell you, sir, before we end, that we are going to have the CFD Symposium, the Nautical Society of India CFD Symposium, this time in BIT Mesra. So after 25 years, CFD Symposium is coming outside of Bangalore. It will be there in BIT Mesra. So 11th to 13th of August, it will be there, and we'll mark our 60th year of celebration. So we'll be completing 60 years of existence in August 24th. So I'm sure I'll actually circulate all the process. Still it is in pipeline. So I'll definitely want that all our alumni should come in BIT on 11th of August.
Oh, that will be great. Yes.
So definitely I'm going to send all the official invites. Everything will be done. We are actually
okay.
I'll try my best to come. I'll try my best to come. Yeah.
So I think we can.
I just have one question to Rajeev Kumar, Dr. Rajeev Kumar. Is anything happening in the hybrid we talked last time?
Yes, sir.
Anything happening to the hybrid rocket? Rocket? We thought we should start some work on the hybrid propulsion,
He's completely working on hybrid only, sir.
Yes, many work I am doing on that.
I think we need to visit once.
we thought that we'll have some discussion with HMRL, and actually we were planning to develop a practical system, so did you talk to them, or has anybody talked to you?
We had a discussion with them. I got a call. I mean, right now I'm not going to share the details on, because it is live right now. We can discuss it on a different call, sir. But I received a call. We have already fixed the stuffs, so it is in the pipeline. So hopefully things will be materialized.
It is on process actually.
Okay.
Okay, so here I would like to take goodbye from everybody and have a nice evening, sir.
Okay.
Sorry. Thank you, sir.
Thank you.
Thank you. We end here. Thank you. Thank you.
Bye.